This here is a 1 kilobyte EEPROM that has an I2C interface, and these devices are pretty common. In fact, I managed to find a few just taking things apart, and you can see here I got a certain number of them now. So let's use an Atmega or an Arduino to extract the information from this and print it on our PC screen. And along the way we'll learn to use the 2-wire interface peripheral by writing our own efficient and lightweight functions for it. Then after that, let's also have two Atmegas communicate with each other to see what other things can be done with this protocol. Now for this video, I'm going to assume that you know the basics of I2C communication. If not, there's a bunch of YouTube videos that talk about this, so I don't feel like just repeating the same stuff over and over. And we can see here's the data sheet of this device. It's pretty simple. It just has the data and clock line. It has an additional chip enable and a write control, so it protects the device from being written by mistake, and then just the two supply lines. Okay, so here's a waveform that shows exactly how to read memory from this device. To start off, we obviously needed a start condition, and we have to call the device by its address and give it a write bit because we're going to tell it the address in memory next that we want to start reading from. Hopefully it acknowledges, and after that it acknowledges again, and we have to create a new start condition at this point because we initially said we were going to write, but now we want to read the actual information. And so this means that we have to select the device once again with the slave address, and this time we send a read bit and it acknowledges, and after that it keeps spitting out all the data that we would like to hear. When we're tired of reading the information, we can just give a no acknowledge bit, and this terminates the conversation. Now on the other side of the line, we obviously have our Atmega or Arduino, and we also have to configure a few things here. This is actually pretty simple and it's quite repetitive, as you'll see. Essentially we have just a few important registers, which are the data register, which contains both transmitted and received data, which is a single byte at a time. Then we have the control register, which by setting and resetting some of the bits inside of it, we can control what the peripheral does. And then we have the status register, which just contains the status of the last operation. So for example, if something went wrong, it will contain a certain value that lets us know exactly what happened. Okay, so let's finally start programming something. Here's a very simple program. You can see there's a few definitions that we'll use. This is a custom library for the UART that I'll be using to print the values to the screen with the terminal. Then here's a few variables. This is just a debugging function that gets called in case there's an error or something and it blinks an LED a certain number of times. It just helps for debugging. Of course, I don't make mistakes, so this won't really be useful. Here we just set up the UART to transmit data, enable an LED. We disable power reduction to the 2-wire interface peripheral, and here we set the prescaler of the peripheral. As a quick comment, you'll see here that I have a 0 after all of these register names, and this is because I'm using the PB version of this Atmega. If you're using an Arduino, then probably this will not compile. You have to just remove the zeros because it only has a single 2-wire interface peripheral. Okay, so let's start very basically. We create a start condition. We wait for the twin flag to be raised, which always happens whenever we do anything essentially with this peripheral. And then we check what the state of the status register is. If there's a problem, then we call our debugging function. After that, we send the slave address. We send the address in the memory of the EEPROM that we want to start reading from. We have to always check to get an acknowledge from the EEPROM. After that, we send the restart condition, as I explained before. We send again the slave address, check for the acknowledgement. We clear the flags, and then here we enter a loop that repeats 1024 times, and this gets called essentially to read every single byte from the memory, from the EEPROM. I won't explain all the details here. You can obviously read the data sheet. So we simply just read the data from the data register, and then here's a little bit of code to transform the values in text so that we can read them in hexadecimal. And then finally we actually send the string, 2 characters, Every time except for the last time we send the acknowledge, enable acknowledge, and instead the last time we send the not acknowledge by simply making sure that it's 0. Probably is 0 already, but just to be safe. And then we create the stop condition, and after that our LED will just blink quickly forever, indicating that the process is over. So let's now upload the code and see if it runs. Okay, so now we're ready to upload the code. Here I have a terminal that will be reading whatever is sent through the UART. I'm using a modified Arduino Nano to convert the UART to USB so we can read it here. And so let's just upload the code. And we can see that this was successful. If we look at the scope here, we can see the start condition and then the slave address and all the stuff that we were talking about before. Just as we were expecting, we can also see it in practice on the actual I2C bus. So this is really nice because we can confirm what we were expecting. Of course, debugging all of this would have been a lot more difficult without my new Fnirsi 2C53T. This handy instrument packs 3 tools in one. It has a 2-channel 50 MHz digital oscilloscope. Then it has a multimeter function that allows you to measure everything you'd expect from a multimeter. And last but not least, it even has a function generator that can turn out to be really handy when testing some circuits. Alright, so let's check out this adaptation using the interrupt service routine before we actually move on to writing some actual functions. And essentially what we're doing here is a case where we have an important task that we have to run all the time. In this case, it just involves blinking an LED all the time, but you can imagine this being some kind of active control function or something like that that has to run almost always. So all we do here is the main basic stuff. It's important that we always activate the interrupt enabled bit, and this means that the interrupt service routine, this here, will be called every single time that the twint bit is set high by hardware. Additionally, here I wrote a little bit of code just to see if there's any kind of strings memorized in the EEPROM, which is just a curiosity of mine. I know this isn't optimal because in general you want your interrupt service routine to be as quick and lightweight as possible, but unfortunately I couldn't come up with a real effective method that's more efficient doing this. So let's try running it. And here you can see that it's printing everything pretty much as we expect. We can scroll up and see, well, there's nothing too interesting as far as strings go. But let's now check the scope because that's the important thing. Let's see if our important task is actually being interrupted and for how long. Here at the top you can see the toggling of that pin for the task, and at the bottom you can see the data line. And this is great because it means that we can take advantage of our CPU a lot more rather than having to wait for everything like we were doing before. Another great advantage of this Fnirsi multi-tool is that it's incredibly portable. It has a fantastic case that holds it safe whenever I'm carrying it around. So whether you need a measurement tool that's really easy to take around with you, or you want to have something that's very compact to keep on your desk, Fnirsi definitely has your back, whether it's with the 2C53T or a range of different instruments that match your needs. So check them out at fnirsi.com/5vlogic for some great discounts on an awesome variety of products. Okay, so the last step, as I said, will be to have the two Atmegas talk to each other. And here you can see that I got a few functions written out. This is basically the code of before, and it's a little bit easier to read and understand. So without going through every single line, you can find this on GitHub, and you can also see that I have a few slave functions. So this obviously will be for the Atmega that will be acting as the slave device. The main function is common for both, or at least a few parts of it are. The first part here is the setup, as we saw before, although in this case we can pass the baud rate as a parameter. Then we also set our output pin for both. This next part here is for the master, and we can see that there's a setup. Then we also need a slight delay to wait for the slave device for some reason. We can send the start condition, call the slave address, and give a read bit, so a 1. Then we ask for 7 bytes of data, giving an acknowledge when we receive them. And then with the final 8th one, we send a not acknowledge back. And then finally we give a stop condition. After that we can just send the bytes in hex on the terminal, separated by spaces and new lines for every time that we try this. This instead is the code for the slave device. Of course, the same setup happens, and then we just have a filling out of the array with the data. We have the slave listen for its own address, and then we loop through forever as long as we receive acknowledges. In fact, whenever this function returns 0, it means that it received the acknowledge. If it returns a 1, it means that it received a knack, as you can see here. So once it receives the knack, it can exit the while loop and go to the common part of the main function, which is where the LED flashes. This will make it so that both devices, when they're done, start flashing. Okay, so let's try this out. First thing we do is send the code to the slave device. Next, we obviously change this so that it will compile it for the master device, save it again, and upload it to the other Atmega. And there we go. We can see that it successfully sent the 8 bytes that we were expecting. You can see here, when it created the data, it was A0, and then it added 1 for every successive byte, so A0, A1, and so forth up to A7. Okay, so this is obviously a very simplistic example, but it should be a base from which you can build more things and expand functionalities by adding other functions if you want and whatnot. And obviously, if you have other important tasks that you're doing, you probably want to use interrupt service routines and some other things that we saw before in combination with these functions. Of course, the whole point of writing these functions is that now we can put them in a separate file that we use as a library, and then all we have is the main function, and we include the library that we created up here, just like I did with the UART. Okay, so thanks so much for watching. Hopefully this was both entertaining and informative, so if you liked it, you can consider subscribing and leaving a like, and see you in the next one.